So welcome everyone. Today we continue to implement our Redis. It's just remote dictionary server. And as you remember in previous video, we just set up our basic structure, which consists of three projects. It's common, master, and child. Sorry, I need to. And what we are going to implement today. In today's video, we're going to implement our child service. I mean this particular child implementation. For sure, we will have a lot of childs, those partitions, and we need to implement the basic behavior for each of them. Okay, let me explain the plan for today. Basically, we are going to implement particular behavior for each partition, and this partition will be implemented via and exposed via RESTful API. We need two main methods for our purposes. These are our add method and our get method. Add method adds some value by particular key, and get value just gets some value by also particular key. But for monitoring purpose and for demo purpose, I will also implement some kind of monitoring method which just returns our snapshot of our internal hash table with every non-empty bucket and entries inside it. Therefore, let me also explain regarding internal structure of our partition. We will keep internal hash table. Probably the simplest way of implementing hash table is just using collision resolution by chain or by using linked lists. What about the value? The value will be in JSON format because it is also the cheapest and the easiest way to implement it in general manner. While you are using and to serialize everything in JSON, you are always working only with string, and you don't need to use some kind of binary data for performance reasons like protobuf or something like that, because they need some kind of prepared structure, and since we don't know what structure of value object will arrive to us, probably the cheapest and the easiest way to implement it is just using JSON serializer, and that's all. But it will use more memory than, for example, binary serializers, but it's up to you. You can implement it via binary serialization for sure. Okay, let's start. Okay, first of all, let me create controller for our child. And now let me implement all RESTful endpoints for that particular child. Okay, let me explain regarding the hash key. Basically, our router in our case will be our master. Therefore, the master should know what partition it should route particular key to. Since we are using partitioning by hash, the only way for master to know to which partition it should send the value is by computing this hash on the master side and then just send it to particular partition, and therefore we don't need to recompute this hash key again in this child. We for sure can do that because the hash key generation behavior will be placed in our common library, but we don't need to do that now. Okay, and for that we need our entry DTO from master to child, which will contain everything we need. Basically, we need key, hash key, and value. Let me restructure this architecture to common application and infrastructure folders. We place our entry DTO because we are going to use it from both master and child. Why? Because in child service we receive this DTO, and in master service we serialize and send this DTO. Okay, now let me implement particular partition service inside the child service. It's just kind of class which encapsulates everything we need for keeping our hash table, get, add, method, etc. First of all, we need to create the hash table for particular partition, and note that this partition will be singleton service, and we need to consider multi-threading and parallel operations here. We decouple our entry DTO from the entry itself, because entry itself is internal model, and in case we put everything in entry DTO and use this entry DTO in application layer here, the entry DTO would have two reasons to change, and this is single responsibility principle violation. Therefore we should split those two independent models. But for now the internal structure of those two models is basically the same. We should keep entry as immutable, because there is no point to change value without changing the key or something else. This should be immutable object. Therefore we protect our setter. Okay, probably I need to explain this. This array of linked lists is our hash table, because we're using collision resolution by chaining, and it contains a lot of entries, and our entry is basically the linked list of our entries. Therefore, by some kind of this index, we'll have linked list of our entries. Why we should have linked list? Because we can have entry with different keys, but they are mapped to the same bucket, to the same index. That's the way how we resolve it. Okay, and entries count is overall count, maximum count of our entries which particular partition can handle. This count should be prime. Why? Because of complex math. Basically, the modulo operator is better for prime numbers. Therefore, if we compute some kind of hash, it's better to apply modulo operator on a prime number. You can refer to a hash table explanation in Wikipedia, for example, or to Corman's book. Okay, we should get our particular items count from configuration. And also we should put some constants in order to place particular literal in one place. Now we can put this variable here, and just we don't to put the literal itself. Here we can just use our global const partition items count name, and we also will use this in our master. Therefore, according to the common reuse principle, we put it in one place. Now this partition items count can be actually not prime number. We will put there a prime number, but it is possible that this value will not be a prime. Therefore, we should ensure that count is prime for better distribution of hash code. And for that purpose, we need our prime number service. You can just steal it from official.NET Core source code. From this one, hash helper, we have there this getPrime method. And also there are a message which we don't need to actually, therefore I just steal it from my own repository. Now we can use our prime service in order to get the closest prime number from particular partition items count current. We initialized our hash table and set our count to 0, but it actually will be 0 anyway. But let's put it explicitly. Now the add method. We will not use asynchronous here because there is no point for asynchronous methods. For sure, if on our add method the actual count is equal to entries count, we should break this operation and we put bigger or equals because of concurrency. It will be safer for sure. And now let me implement the custom exception. In that case, we will handle it in next series for sure. We don't have time to that in this series. Just standard exception pattern. Okay, if our count is overflown, we throw exception. Got it. And then we just try to find our particular bucket for particular hash code. And for sure there is the case when this entry will be null, because since we have our array of linked list and linked list is a class itself, the initial value for this for each index will be null. Therefore we can ensure that this value is not null because we are going to insert to linked list. And now, since we can have concurrent methods on add, and it is possible that two different keys will collude to the one particular node, and it is possible that two concurrent threads will try to initialize this particular bucket with new linked list, and this is not okay. Therefore we can use lightweight synchronization mechanism called interlocked. It will not go to kernel mode. It is needed here for ensuring that initializing our new linked list will be done only once. As the first parameter we put our ref location here, ref for particular index. We try to insert our newly initialized linked list and we compare it with null. And let me explain a little bit what this code actually does. It sends particular instruction for compare exchange operation which the processor will do at once, or aka in atomic fashion. What actually this method will do, it gets this particular index and try to set new linked list to this particular index only and only in case if the value by this index is equal to null. That's all. We need to ensure that this will be done only once, because in case two threads go to this method and we didn't use the interlock compare exchange, it is possible that we will initialize it twice. But then what we are supposed to do here is just to lock this value, and I'll explain why it is necessary here. Why? Because actually we under this index we have our linked list which is not thread safe, therefore we should not allow concurrent access to this linked list. I mean, when we get two threads is adding at the same time, it is possible that they go to particular add method for linked list also at the same time, and it can break something. Therefore, we safely lock it, lock particular entry here. For sure, for other entries, it is allowed to insert. It is not allowed for the values with the same hash key. So it should not harm performance a lot. Okay, we're going to go through the each key in by that particular hash key, and if some entry key is equal to our particular key which we are going to insert to, we throw new exception because we actually try to insert value with the same key which is already existed. And if we go through the whole chain of nodes in linked list, then we safely can add our entry to the end of linked list. And for sure we increase our count. Yes, probably this operation can be done from multiple threads. It is atomic operation, increment, or maybe even not. Probably we can do it also with interlocked increment count, because yes, there is a possibility that this count will be incremented by multiple threads at the same time. Okay, that's all for our add method. Let's implement the get method. And after we get particular bucket, we just try to find the entry with this key. Okay, explanation about this method. We just get particular linked list, and this linked list contains only the values with this hash key, but at the same time these values should have different keys and may have different values because they are collided to this particular bucket, and we ensure that they have different keys by this. It protects us from having the same keys. And therefore, if some entry's key has the same key as our key which we are going to get by, then we return this entry value. And now let me implement this last method for monitoring purpose. Basically what we are doing here, we get our entries, which is an array of linked lists. We ensure that every linked list is not equal to null, because by default after this initialization every single index have a null, because linked list is a reference object. Then what I want to do here is just get all the entries by particular hash key, and then we just select our hash key. Since each bucket has basically the same hash key and every entry in the particular linked list have the same hash key, we can just grab first entry's hash key. And also, because I would like to know the particular index in our entries, we should perform modulo operation, and after that we just put here our linked list, therefore the list of all entries by that bucket. And now we can just use this service here. Oh no, we cannot, because we should extract the abstraction, because dependency inversion. Now we should di everything here. We use singleton because we need to keep the one and single instance of partition through the all lifetime of the application, because this instance contains every data and we need to keep it durable by the life of our application. Also, we should di our prime number series. And now we should place it in some kind of convenient DTO. This bucket DTO is actually the same what we return from the partition, but in partition we return just list of tuples, and here it is like implemented module for network transferring.
It should be obvious to you that if anybody wanted to kill the president, he could do a beautiful job of it. By 7 o'clock tonight, we'll be out of the country and you'll never see us again. Let me show you something.
And the get and add method are trivial ones. Now also let me add Swagger in order to show you demo. Okay, we got our Swagger, and now let me add something here. We can just generate random hash key. It will be calculated in master, some random key and some random value. Did I put the breakpoint? Okay, now we shoot the breakpoint. Let me show you our entries. It's our hash table. As I said before, everything is null now. Okay, we got particular entries, bucket, and it is equal to null for sure because everything is null now. Compare exchange. Right now, some entries should not contain null. Here's 68. Now we log particular bucket. There is no any entries now by that bucket. And then we just add last it, increment count to 1 and go out. Let me show you this method. Partition entries. Yes, our bucket index is equal to 68 with particular key, value, etc. If we try to insert with the same value, we should get exception. Yes, because it is already exist. But if we get object with the same hash key but with different key, it should be inserted, but it will be collided. But since inserted, yes, it was inserted, and now we just have two entries by particular key, the same as in each hash table. If we insert this by different hash key, it is inserted, but it goes to different bucket. Okay guys, something like that. Thank you for your attention and goodbye. In the next series we'll implement master service.